Now in this video, we want to determine the three questions that I asked in the previous video. If I'm given an initial velocity and an angle, I want to know what the total time of flight is, what is the maximum height the object reaches, and what is the range, what is the distance, the maximum distance that it reaches along the x-axis. So if I know those things, then I know essentially everything there is to know about this problem, right? Mainly, I want to predict exactly where this is going to land, all right? Now notice, okay, we talked about the components VIX and VIY in the previous video, but what are VIX and VIY? Well, notice I have a right triangle here, and the hypotenuse is VI, VIX is the adjacent side, and VIY is the opposite side. So VIX and VIY are related to the actual initial velocity via the trig functions cosine and sine. So now in the previous set of equations, anytime I have VIX, I can insert VI cosine theta, and anytime I had a VIY, I can insert VI sine theta. So let's tackle the first question. Maximum, or what is the total time of flight? Let's tackle total time of flight. If you recall, before, when we just tossed something upward, we calculated the time of flight by finding the time it took to rise to the highest peak and then doubling that, because we know that it's going to take the same amount of time as it does to rise as it is to fall. So if I can find the time that it's going to take to reach that peak, then I can just double that, and that will be the total time of flight. Now, here's something that is very fundamental to this problem. Again, at the peak, the velocity in the y direction is decreasing, but because there's no acceleration in the x direction, VIX is constant throughout the entire flight. So at the peak here, even though before we said if I just toss something straight up, the velocity at the peak is 0, in projectile motion that's not necessarily true. At the peak, the velocity in the y direction is 0, the velocity in the y direction is 0, but the velocity in the x direction is constant. But we can still use this because we can break these up into our components. All we have to do is look at each component individually. So what I can say is that if I want to calculate the velocity in the y direction at any given time, I start with this equation. And this is nothing other than V equals VI minus AT. Okay, and again, I'm inserting the minus sign because up is positive and gravity is downward. And the VI sine theta is just the initial velocity in the y direction. So the velocity at any point in the y direction can be calculated if I know what time I can, or what time to plug in. But it turns out time is what we're solving for. Again, in the y direction, okay, my velocity is going to be constantly decreasing as my projectile rises, and at the peak, the velocity in the y direction will be 0. Okay, the velocity in the y direction will be 0. This is why breaking the problem up into its components is so useful. So, if at the peak Vy is 0, then all I have to do is say this: 0 is equal to Vi sine theta. Oops. Let me make that a little bit better. Minus GT. And if I solve this for t, I get Vi sine theta divided by g. So my total time of flight is going to be double this. Okay? This is the time that it takes the projectile to reach the peak, and then it's going to take another equal amount of time to come back down. So my total time is going to be 2 times that. So that is the total time of flight. Now, what about the maximum height? Okay, well, I can find delta y max from the second kinematic equation, right? I can find delta y max from the second kinematic equation. And let's put this over here because we're going to use it. All right, 2 vi sine theta over g. Now, the maximum peak can be found from this equation. Let me scoot it over a little bit. We'll run out of room if I'm not careful. So delta y max is going to equal vi y t minus 1/2 gt squared. So we'll start here, okay? Now again, VIY is just going to be VI sine theta. And t is going to be the value that we found to get from here to here, which is just going to be half of this, or VI sine theta over g, okay? Again, this is the total time of flight. At delta y max, right, this is half of the total time. So I'm just going to get rid of this 2 when I plug in for t up here, all right? Hopefully that's not too mysterious. So delta y max is going to equal VI sine theta times t, which is VI sine theta over g, all right? And I'm going to put the next part of the equation below here because I'll run out of room if I don't. So this is then going to be minus 1/2 g times VI sine theta over g, and that's squared, right? Now, this is pretty busy, okay? So let's break this down. Here I have a VI, and here I have a VI. Here I have a sine theta, and here I have a sine theta. So on my numerator here, I'm going to get VI squared times sine theta squared divided by g. So this is going to equal, the first term is going to equal VI squared times sine squared theta over g. And I'm then going to subtract this term. But notice, here I'm going to have a VI squared, and here is sine theta squared. And I'm going to get a g squared on the denominator here, and that's going to cancel with with this g, and then I have this divided by 2. So this is going to be VI squared sine squared theta divided by 2g, right? Now, these are very, very similar. This is the same thing as having a quantity minus the same quantity divided by 2. So this is essentially saying 1 minus 1/2. So if I take this and I subtract this, I get half of this, because this is half of this, so I just have half of this left. So my total range, or my maximum height rather, is given by this, okay? So this was the total time of flight. We plugged in half of the total time of flight for t into our second kinematic equation, and that allows us to find the maximum height that the projectile reaches. Now again, why are we doing it this way? We want to know what the maximum height is going to be if I'm only given the initial velocity and the angle. So all of my formulas should only depend on the velocity and the angle. And in fact, they do. My initial velocity is here, my angle is here, and again, g is constant. So that is perfectly fine. Now, what about the range? Okay, how can we find the range? The range, well, again, there is no acceleration in the x direction. So if there's no acceleration in the x direction, then delta x max is going to be equal to Vix times my total time. Times my total time. And so delta x max is going to be Vi cosine theta times our total time of 2 Vi sine theta over g. And what does this turn into? Well, here I have VI and here I have a VI. So I have VI squared, and then I have a 2 times a cosine theta times a sine theta. Oops. And this is all over G. Now, here's a fundamental property from trigonometry. This is one of your trig identities. 2 times cosine theta times sine theta is the same thing as sine of 2 theta. So my delta x max is going to be equal to VI squared times sine of 2 theta all over G. And so now we have seen the three properties that I wanted to find at the beginning. I wanted to find the total time, which we have found. I wanted to find the maximum height that the object achieves, and we found that to be VI squared sine squared theta over 2G. And now I found the range as VI squared times sine of 2 theta divided by G. So whatever my angle is in here, I multiply that by 2 and then take the sine of that total angle and I'll divide that by G, and that will give me the maximum range. As you may have guessed, okay, the maximum range, if for any given angle, right, if I have a given launch speed and I can adjust the angle, okay, what angle is going to give me the maximum range? The intuitive guess is 45 degrees, and in the absence of air resistance, that is absolutely correct. If I plug in 45 degrees here, 2 times 45 is 90. The sine of 90 is 1. Sine ranges between -1 and 1. And so whatever value gives me 1 here is going to give me the maximum value for my range, and 45 degrees is what does it. Okay? So that is how to apply these problems to projectile motion.